Let's review roots with powers other than 2, something other than a square root. I think a lot of you have gotten used to doing square roots without kind of thinking about what you're really doing. It's just kind of a knee-jerk reaction. Okay, the square root of 9 is 3, the square root of 25 is 5, and you're not realizing that when you're doing the square root, the reason why you're getting those answers is because technically you're looking for things underneath the radical, underneath the root, that are perfect pairs. You know, a square root is you're looking for 2 of them. So then when you do a cube root, you're now just looking for perfect triples. And a fourth root, the same thing, you're looking for perfect sets of 4. And if you think about it that way, then roots of all powers end up being the same thing, and you kind of attack them with the same mindset and the same set of steps, and it doesn't feel like you're learning a completely different technique to do a cube root or a fourth root or a fifth root than you did with your square roots. Okay, so let's look at a basic square root problem just to remind ourselves of how this works. So let's say we're going to do the square root of 50x cubed. Pretty simple, right? Well, you'd think, all right, well, 50 is 2 times 25, and 25 is 5 times 5, and there's my perfect pair. And then the x cubed piece, of course, is x and x squared, and then you can look at x squared and go, yeah, that's my x and x, there's another perfect pair. I'll say, so now that I've found these perfect pairs, I know that when I take the square root of it, I only get one piece of the pair, right? I get just the 5 and the x on the outside, and then the other half goes away. That's basically what's happening with the square root. But then what's left over? Right? We still have this 2 and this x that weren't involved in these pairs. And so those are still left on the inside of the square root. Simple, hopefully. Now, when we do a cube root, the idea is the exact same thing, only instead of looking for perfect pairs, we're looking for perfect cubes. So again, we can start with a constant and go, okay, this is 2 times 4, which is 2 times 2, and you go, hey, look at that. A perfect cube, right? Well, x cubed, do we even need to bother with that, right? That's x times x times x. That's a perfect triple, right, of 3 x's. And then this one, we can do, well, how about y to the 4th and y to the 8th, because remember, when you have y to the 4th times y to the 8th, you add 8 plus 4 is 12, and then this is y to the 4th and y to the 4th, and there's another perfect triple. So this one, there's nothing left on the inside, right, because the x's were also perfect, and so all you're left with is 2, right, one of the 2's, the x, right, because remember there were 3 x's here, x, x, and x, when we found that perfect triple, and then when you've got your triple of y to the 4th, you have y to the 4th, and everything else is gone. So this one was a perfect example of a perfect cube. And the idea is, if we now took this thing and cubed it, right, we would get back to what was on the inside. 2 cubed is 8, x cubed, right, and then y to the 4th cubed, and so we've checked it, and yep, the works out. So it doesn't matter if it's a cube root, a fourth root, a fifth root, whatever it is, you're looking for these perfect triples, sets of 4, sets of 5, and when you're dealing with powers, it's really easy because a cube root is really the same thing as a 1 over power. So let's look at another example. How about something like this? We've got the 4th root of 48 x to the 5th y to the 8th, z to the 18th. Well, this is really the same thing as 48 x to the 5th, y to the 8th, z to the 18th, all raised to the 1 over 4, or 1/4 power. That's what a root really is. It's really a reciprocal of a power, right? Roots undo powers. They're reciprocals of each other. They're inverses of each other. So it's a 1 over 4 power. And when you have, if you remind ourselves, we'll remind ourselves over here on the corner, if we have x to the m raised to the n, right? We have a power raised to a power. What do we have? We multiply them, m times n, right? If we have x to the m over x to the n, that's where we subtract them. And then we already saw, we remind ourselves over here that when we multiply, we add x to the m times x to the n is addition, m plus n. Those are our basic rules of powers, rules of exponents. And so in this case, we have all of these things that are being raised to a power, right? Power to a power. So you're going to multiply them. And you really end up having 48 to the 1/4, we can deal with that later, x to the 5/4. And then y to the 8 times 1/4, isn't that just y squared? And then z, 18 divided by 4. Which of course you can simplify to 9/2 if you want to. But it's probably better to leave it as 18/4. And then really the best thing to do is to think of it in terms of a number and a remainder, right? 18/4 is really 4, right? 4 times 4 is 16, and 2/4. The same thing with this. You'd want to think about this as 1 and 1/4. And I'll show you why. All right, so 48 x to the 1 1/4 y squared z to the 4 2/4. Now I know you're all yelling at me, 2/4 is a half, simplify it to a half. Yeah, but you want to leave it as 1/4 because we want to be able to put this back in terms of the original radical, which was the 4th root. Now you don't have to do it this way, guys. If this is confusing the heck out of you, then go back to what we did up above and just find those perfect fourths, right? Find a set of 4, and 1 goes on the outside, the rest go away, and then if there's anything left over, it's left over. And in fact, I'll do that after we're done with this one. I forgot this is still to the 1/4. Okay, the 4th root of 48, we're looking for those perfect fourths. So 2 and 24, 2 and 12, 2 and 6, 2 and 3, and then there's my perfect 4, and that's what's left over. So that means on the outside I have a 2, and on the inside I still have that 3. Okay, my x's, I have 1 and a 4th. That means I have 1 on the outside, and then the 1/4 means I have 1 on the inside. My y squared, I have 2 of them on the outside, and there was no fractional remainder, so nothing on the inside. And then my z's, 4 and 2/4, I've got z to the 4th, right? And then on the inside, sorry, how many do we have left? Those 2. That's why we left it as the 2/4. And there's our answer. See, that's the beauty of dealing with it with this 1/4 power, is it kind of makes it easier. Now, if you wanted to look for those perfect, sets of 4, then just do the same thing we did here with the number with the other things. So, for instance, with the x piece, you just have x to the 5th, right, which is x, and you just keep going, and you'll get 4x's here, and then you'll have that 1 left over there. So you'll have a set of 4 and 1 left over x. Right? With the z to the 18, with 18 of them, you can kind of ask yourself, what's the largest number that divides into, doesn't divide into, the largest multiple of 4, sorry, that is still smaller than 18? You go, that's 16. Right? Z to the 4th, z to the 4th, z to the 4th, z to the 4th, there's my 16, and then 2 more gives me 18. So there's z to the 18th. And then here is my set of 4. So however you want to think about it, it's still the same thing as dealing with a normal root. You're just looking for sets of something instead of with a regular square root you were looking for pairs. I hope that helps.